relativistic particles from the Sun. This talk is included in the session HR2, Historical Supernovae. Is the historical section of the Marcel Grossman meeting with the aim to understand the historical phenomenon of the 1054 supernova, the Chinese supernova. But this starting point, solar physics, is required. Why? I want to show the strongest source energy that we have nearby of high energy particles, high energy physics, and this source is the solar flares, is characterized by this phenomenon, the eruption of particles and radiation from the Sun through the mechanism of magnetic reconnection. Here we have a plot of the X-ray radiation in two bands, long and short X-rays. The waveband is between 1 and 8 angstrom, and so they are X-rays. And here, in particular, I have plotted the last flare observed from our hemisphere before writing the PowerPoint. And this is a flare of class C4, so not very big. There is another one a few hours before reached the class M, but it is representative of the phenomenon. The decay of the flare is almost similar between the various phenomena. The duration is about 20 minutes, and the intensity and the integrated flux is automatically detected by the system, the informatic system of the Space Weather Prediction Center of NOAA, the National Oceanic and Atmospheric Administration. The flux is expressed in watt over square meter, and the class of X-ray flare is standardly divided into C and X, and the more modest A and B, through a 10-fold scaling. Well, the biggest flare can have a luminosity of 100 in the class X. The largest one is about 50, recorded in the last 50 years, but there are indications of flare even larger, like the one of Carrington event. So we can imagine the range going to the top of this plot, to the 10 to the minus 2 watt over square meter. And then the integrated flux scaling it, this one to the biggest one is about units of joule over square meter. What this energy is for? The stimulation to deal with such event of solar physics, which can enter the domain of relativity, because the velocity of the protons is nearly the velocity of the light, is the most energetic phenomenon as the explosion of supernovae or gamma ray burst, like the one that we considered the source of the Chinese 1054 supernova. If it was a gamma ray burst at 2 kiloparsec, these are the calculations starting with a gamma ray burst chosen as reference of 10 to the 51 erg per second at the starting point, at the distance of 2 kiloparsec, when it is viewed from the Earth, its luminosity should be even 1,000,000 times stronger than a solar flare, and probably 10,000 times stronger than a Miyake event. Let's say the order of magnitude is 1,000 than this particular event, which is a super flare occurring about each 10 to the 4 years. The flux is estimated around 10 to the 4, 10 to the 5 watt over square meter, and the integrated flux for the first 30 minutes is about 10 to the 3 joule over square meter. So from 50 to 500 times the X100 flare event. It has been studied that the safety zone for the life is within, outside the 15 kiloparsec from a gamma ray burst. These studies are very old, but we know why, because of the Cold War, which was at that time very hot, dealing with nuclear weapons experimented in the atmosphere. The solar X-rays can penetrate the atmosphere, we see here, around from 45 to 100 kilometers of altitude. It depends on the wavelength and the transparency of the atmosphere. The UV radiation is screened by the ozone layer to higher levels from 160 to 35 kilometers, while the solar protons, depending on their energy in mega electron volts, can reach even 8 kilometers of quote, while the lower energy particles can reach only 90 kilometers of quote. The alpha particles, the nuclei of helium, can penetrate to higher quotes, up to 25 kilometers. The electrons to 10 kilometers of quote, and the Bremsstrahlung radiation is capable to get 30 kilometers of quote. In this note, it is written that the CO2 absorbs the maximum quantity of infrared radiation, but the major part of the radiation of the sun gets the Earth from wavelengths larger than 700 nanometers. So this is the response of the atmosphere to high energy radiation, even to particle radiation, and it has to be considered in the effects to biological systems, as is expressed in the tables of NASA and of NOAA to classify the geomagnetic storms. The problem of space weather is mainly for astronauts and for satellites. For us on the ground, the question is if we can see a spectacle of boreal aurora or not to low latitude, like Pescara. I analyzed the last event of a coronal mass ejection produced by a solar flare. Is the one of 8 June 24, 1 month ago. There was a tribal flare in about 1 hour and a half, peaking to class M9.75, which is almost X1. The flare was expelled, the coronal mass ejection was expelled from the solar limb, but reached the Earth, and the light of the peak arrived around 1:38 a.m. UT of June 2024, 8, and the protons arrived about 22 minutes later. Afterwards, there is a difference between the energy of the protons. The most energetic ones are the one represented with green, and the less energetic ones are the red one. But in any case, they are particles. It's a particle radiation, and the delay is 22 minutes after the light. So the velocity, if the light was 8.5 minutes, light minutes from the sun, the protons are 8.5 plus 22 minutes of time required to arrive to the Earth. In these images, in this animated GIF, we have the proton arriving to the SOHO telescope, the coronagraph C3. This is active since 1995, and this snow is the arrival of the energetic particles, which is about, the big part is about 2 hours after the coronal mass ejection, while the coronal mass ejection is still near the sun, within a few solar radii. This is the sun radius. The coronal mass ejection is not yet to more than 6 solar radii, then that the snow is already arrived at the Earth, or at the position of the satellite, so which is 1.5 million of kilometers from the Earth. So this is the situation, and from this video also we understand the velocity of these particles. From the previous plot, we can estimate the maximum velocity of the protons like 8/30 of the velocity of the light. So the energy is between 100 and 500 mega electron volt. It's 40%, 30% of the velocity of the light, 27%. Just to remember the amount of energy available for the phenomenon of magnetic reconnection, the largest magnetic fields in the solar spot have been evaluated around 6,000 Gauss. The dimension of the line of forces involved in this phenomenon can be around 10 to the 8 meters. So the energy is the magnetic energy multiplied by the volume of the involved region, while the case of gamma ray burst is completely different, because the gravitational collapse is the source of the energy, including the rotation, the fast rotation of the object. Do we have some events recorded in the atmosphere through the isotopes analysis, which is related to the event of 1054? Yes, there are some data in the Antarctic ice core, in particular the Fuji dome analysis, and they are data integrated over 20 years, so the channel of time integration is 20 years. Here we have an example of what can happen if the magnetosphere of the Sun, so the heliosphere, is stretched and compressed by the passage through an H cloud cold, and it is probably the case of 3 million years ago, when the magnetosphere of the Sun is less active. There is a major quantity of cosmic rays, and so more isotopes in the sample studied, and these can be events of this kind of situation. Analogously, when the Sun is at minimum activity, there are more cosmic rays, and this is the analysis of the 5 solar minima detected through the analysis of ice cores, in particular the Dome Fuji in Antarctica. So we have the periods of minima in which there is a maximum presence of isotopes of beryllium-10 with the following characteristics. So the maximum presence is at the minimum of solar activity, and if the solar activity is 120 years long or 70 years long, like the Maunder minimum, this one, the peak is in the middle. We have the peak at the end only in the case of the so-called Oort minimum, and these points represent 20 years of average. This is, according to a possible view of the phenomenon, a track of the supernova or the gamma ray burst occurred in 1054 in the Crab, originating the Crab Nebula. So an indication of this phenomenon can be found also in the analysis published in the Antarctica studies. These are different publications and different studies which are converging onto this feature, a peak just after the solar minimum instead of the peak in the middle of the minimum, as for the all other 4 minima, grand minima of the Sun. We know that the Sun is experiencing grand minima for a fraction of its astrophysical life, like about 10%, and 10% the grand maxima, and the rest is average behavior. It occurs that in some events, the so-called Miyake events or super flare, there are single events, very, very strong, but these single events in this kind of study are averaged on 20 years, and then they are less visible than and this event occurs for only tens minutes, 20 minutes, as the flare and as the initial phase of a gamma ray burst where the big energy is irradiated. Thank you for your attention.